Thank you, Zen, for your introduction, and welcome everybody to today's webinar. So the topic today is the importance of moisture in pharmaceuticals and food materials, analyzing surface area and activation energy of diffusion studies. So in the presentation today, I'm going to go over an introduction of two techniques, iGC-SEA and DVS. And then I will go on to talk about the methods experimental methods we carried out, and some results. So first I'm going to talk about iGC-SEA. So this is Inverse Gas Chromatography Surface Energy Analyzer. So the IGC system was first developed in the 1950s, and it uses vapor molecules to analyze a material. Since then, surface measurement system has improved this model and introduced surface energy analyzer. So it was specifically designed to determine the surface energy and heterogeneity of samples. And from this, we can obtain different parameters such as adsorption, isotherms, heat absorption, glass transition temperature, solubility parameters, and a few others as well. So comparing to our traditional analytical gas chromatography, this is where we have unknown mixture of gas vapors in a known column, and by interacting with the column, we can separate out the vapors and obtain different retention time for each vapor injected. However, in the case of inverse gas chromatography, the technique that we're looking at, we have our column packed with our sample of interest, and we're injecting known molecules. And from the interaction with our molecules and our sample, we obtain different retention times. From there, we can analyze the peaks and obtain different physicochemical properties. So when we're looking at analyzing a material, there's a few things that we can possibly answer by using different techniques. So what does material look like? For this, we can use spanning electron microscopy and other microscopy methods. And we can also maybe understand what the material is made out of using techniques such as XRD, EDS, and EELS. And on this side, we're looking at atoms in the center and in the bulk of the material, which are surrounded by other atoms. And on the other side, if we want to understand factors that affect how a material interacts, this is where IGC can come in. And in this technique, we can understand the interaction of other materials with the sample. We're able to quantify the ability of the surface to react. We're focusing more on the iGC-SEA side in this SEA technique in this presentation. So on the right-hand side is an iGC-SEA system. As you can see, there's a door in the middle and two drawers that open up. So each drawer occupied by 6 different reservoirs, and this is where you put your gas vapors and your solvents that you wish to use for analysis. And typically, we have some non-polar and polar probes we introduce into the system. And this is very useful, especially when analyzing surface energy. We need a mixture of both to obtain kind of dispersive surface energy and specific surface energy. Each system has a carrier gas of either helium or nitrogen. And in the middle, we have our columns. So we have a 2-column oven system. So our packed column goes in position 1 and another one in position 2. And it's surrounded by a column oven. And the column oven can go from 20 degrees to 150 degrees. In the system, you can also measure background humidity. So in this case, one of the probes will have to be water. You can introduce humidity onto a surface and analyze its properties based on this change in surface. We use a flame ionization detector to detect all our solvents, and this is particularly useful in obtaining very accurate readings of organic vapors. Of course, we have safety features such as hydrogen leak and organic vapor leak detectors also. Our in our iGC-SEA system, we can measure a different range and variety of samples. So here at the bottom, we can see a few examples. We have carbon fiber, cotton, hair, granules, powder, and so on. So it's very diverse, and we can actually analyze a lot of different types of samples. The system has two softwares. One is a control software, so this is directly linked to our iGC-SEA system, and this is where we start to make our experiments and program them into our system. We also have an analysis software, and this is where you analyze your peaks, so you obtain retention times, where you automatically calculate different properties. And as you can see from a few of the tabs at the top, there's a few different things that we can do with the SEA. So we can measure surface energy, isotherms, and BET, surface area. So we can do a different range of different types of analysis. And it's important to note that it's an automatic analysis, so it doesn't require much input from yourselves. And we can also generate reports also for each different method and each different measurement. So before starting a experiment, first what we need to do is pack a column of interest, and then we need to select different probes. So we can select, with regards to maybe a surface energy experiment, some non-polar probes, which are useful for the dispersive interactions, and some polar probes for the specific interactions. We can then choose how to inject them. So we can inject them at very small concentrations, at infinite dilution, and also at larger concentrations. And from the interaction with the sample, we will obtain different retention times. And from this, we can analyze these peaks and obtain different physicochemical properties. So to pack a column, it's fairly simple with respect to our standard GC column. Our columns look like this, a silanized column. And effectively what you'll do first is add some silanized glass wool and put into the column your sample, and again plug the top with some more glass wool. This just ensures that none of our sample goes into the system during the experiment. We have different column sizes. We have 2, 3, 4 millimeter columns, and these are for maybe the 2 and 3 is usually for powders and granules, and 4 millimeter columns are for fibers and things like paper that you wish to kind of chop up and put into your column. The 10 millimeter column requires a specific oven size, but a 10 millimeter column is useful for carrying out experiments with whole samples. So let's say a whole tablet or a block of wood. So it's quite useful. That's something that you don't wish to break up further. We also have a YouTube clip showing you how to pack a column. It's fairly straightforward if you're interested in that also. So there's a few benefits of using iGC-SEA. First is the 2-column position oven design. So effectively what you can do is we can run the columns sequentially and automatically. We can have up to 10 methods onto our software, so we can run them automatically. There's no need for any outgassing facilities. So in our system, we can do in situ column conditioning. So in this case, we don't need any third-party outsourcing facilities next to our system. Column packing is relatively straightforward, and because we're injecting vapor, molecules, our injectable amounts are very precise, and we can inject a wide range of different concentrations. And our injections are all automatic, and with regards to our results, we have excellent reproducibility, especially in the case for surface energy. So one of the things that we can do with the iGC-SEA is to analyze our BT-specific surface area. So in this case, what we have as an example is our a reference CRM aluminium sample, and here we have 500 milligrams. And if you look here, if we have our reported value and our value obtained from iGC-SEA. So in this case, we've injected octane molecules into the system to calculate the isotherm and BET. So this is the corresponding isotherm. It is in the BET range. And this is our corresponding BET plot. And as you can see that there's a good agreement between the reported value and our value obtained by the iGC-SEA. So I'm going to briefly introduce the DBS system. This is dynamic vapor sorption. So to analyze materials, there's a few ways, different types of probes you can use to analyze. We can use energy as a probe. So in this case, an example would be spectroscopy, such as light spectroscopy or X-rays and lasers. And this is useful to obtain any analytical and structural information. We can also use heat as a probe, and for this example is a calorimetry. In our case, with regards to the DBS, we use molecules as a probe. So this is more looking at sorption techniques, and more thermodynamical, chemical, and structural information can be obtained using this method. So really what we do is we introduce a particular vapor molecules into our material, and they can either absorb on the surface or molecules can be absorbed into the bulk. So this process is the process of sorption. We can also measure desorption, so when these molecules leave our sample. So with regards to molecules being absorbed, we're looking at molecules on the surface. And these gives rise to physisorption and chemisorption interactions. With regards to molecules being absorbed into the bulk, this is more bulk sorption, and we can understand how these molecules have interacted in the bulk and in the lattice structure. So with adsorption, we have two types of interactions. We have physisorption, and these are weak interactions, and the molecules are not chemically bound to the surface, and this can give rise to reversible sorption. And there's a few properties that can be obtained from this, and these are structural properties, for example, surface area and pore size. We can also understand chemical interactions, for example, hydrophobicity and surface heterogeneity. We can also understand thermodynamic properties such as heat absorption and free energy. We also can have chemisorption. So in this case, the probe molecules usually have stronger interactions, and they're more covalently bound to the surface. So this can, as a result, cause reversible or irreversible sorption. And a few properties attributed to this is active surface area or titrate acid-base sites. So next we're looking at more bulk sorption. So this is the absorption properties. And this, in this case, molecules tend to penetrate into the surface. And this penetration is often diffusion limited. So this can correlate to a reversible or an irreversible sorption. And again, we have a few properties that we can obtain from this kind of bulk absorption. We have structural properties, so we can have a look at the glass transition temperature, crystallization, and deliquescence. We can also understand total sorption capacity and solubility parameters. And because it is a diffusion limited interaction, we can also understand the kinetics. So diffusion coefficients and looking at maybe drying kinetics. So we can also have absorption into the lattice structure. So in this case, it's possible to have a look at solvate formation. This can be irreversible or reversible. So the associated properties with regards to this is the stoichiometric hydrate or solvate properties, and understanding kind of the channels and the solvate channels in the system. And again, we can also have some kinetic properties measured as well. So here we have an example of what's happening in the DBS. So a DBS is a gravimetric technique. It's continuously measuring the mass of your sample. So in the system, we have a balance. We have a reference pan and we have a sample pan. So our reference pan stays empty, and our sample pan has the sample that we're wishing to measure. And what we do is we introduce some molecules, in this case, water molecules, into the system. And as a result, this is what we obtain. So we have a few parameters. We have temperature, time, and weight. So here in the purple is our experimental method. So here we are increasing, let's say, each step by 10% relative humidity. And before going on to the next step, we have to reach a level of equilibrium. So once this is reached, we'll go on to the next step and so on. So in this case, it's looking at the sorption properties. And the reverse phase, we can also look at the desorption properties when the molecules are leaving the system. So in this case, we've mirrored our sorption and decreasing in the same manner. Our red line is our experimental data. So at the beginning, we may have a drying period where we want to actually dry our sample, so we have no kind of adsorbate on the surface, which may cause maybe a few differences in our results. So it's best to dry the system initially. And again, we have our sorption profile and our desorption profile. So all the time, our DVS is measuring the weight of the sample at each time. So the DVS can be compared to a more static method, a jar method. And in this case, what you would need to do is have a separate jar for each different relative humidity that you'd like to measure. However, in our system, we just have one instrument which can handle all different levels of relative humidity. In the jar method, we have very slow equilibrium to be achieved, and this is only using Brownian motion. However, in our system, we can have a gas flow of up to 200 milliliters per minute, and this and with this we can obtain fast equilibrium. So, as a result of this, our experimental time can be considerably shortened. So with regards to the static jar method, to obtain a single data point, it can take weeks or even months. However, in our case, the whole experiment can take less than a day. There's also differences in the amount of mass that we can use. So the jar method, we need up to from 1 to 100 grams of the sample. However, in our case, we have sensitive balances, so we can use very little sample, from 1 to 10 milligrams of sample. Also, with the jar method, you need to remove the sample each time and weighing it each time to obtain data points. And of course, in this case, you have a risk of contamination or sample loss. And in this case, it can take a very long time just to get one single data point. However, in our case, the sample is measured constantly and weighed throughout the experiment with no contamination or loss of sample. And for this reason, we can have very short experimental times. With the jar method, we are only able to obtain information about the sorption curve, and it's not possible to actually measure any desorption characteristics. However, in the DVS, we can measure sorption and desorption and obtain more information, especially with regards to the hysteresis gap between the isotherms, and this between the sorption curves, and we can understand maybe the kinetics and morphology changes much more better with the system. So this is a schematic of one of our DVS instruments. You have a sample pan and a reference pan, and these will be these two here. We also have both pans attached to a microbalance. We have two mass flow controllers, so we have air, dry air, and nitrogen, and we also have our probe mass flow controller also. So in this case, it's a water reservoir. So these can be flowed through our system. So what you do is we take our sample and place it into the sample pan, and from here we can actually attach a preheater. So that would be underneath this space here. So we can attach a preheater and we can preheat our sample prior to any experiments. So in the case study, we're looking at how moisture can affect the properties of some materials, and what can be the effect of too little or too much moisture in a complex organic material. So in the case of some food samples, we have, for example, potato crisps, and introducing humidity can lose their crispiness, and it kind of decreases the glass translucent temperature of the crisp. With regards to crystalline pharmaceuticals, hydrates can become very dehydrated, and thermodynamic stability is compromised at low relative humidities. Similarly, with proteins, at low RH, they can actually denature and lose their biological activity. With regards to freeze-dried powders, they can transform into liquids and maybe form amorphous solids and deliquescence-forming solutions. With regards to free-flowing powders, when you introduce humidity, what can happen is it can turn into kind of rigid solid cakes, and the amorphous solid can crystallize and have high moisture content. With dry powders such as aerosols, when you increase humidity, they tend not to disperse, and particles would adhere to each other, making them quite poor in their behavior. So now I'm going to have a look at our case study. So in this case study, we are looking at using iGC to determine the surface area, and DVS for some sorption measurements. So moisture has a large impact on the mechanical, physical, and chemical properties of materials. And the drying process can be found in key production stages such as crystallization, wet milling, granulation. And this can improve stability and prevent deterioration of drug compounds. It can be useful to prepare a granule for tablets and formulation, and is very useful to understand if the product will be good for easy transportation. Introducing humidity can have physicochemical stability effects, and it may convert some samples into amorphous samples, or they may become chemically labile. As mentioned before, it can also affect flowability, because water can actually cause condensation inside the bulk of the material and cause forms interparticle liquid bridges, affecting the flow behavior of some powders. So in this case study, we're looking at starch samples. The starch samples we're looking at are starch samples that have been gelatinized. So in this case, we are looking at partially gelatinized samples and completely modified starch samples, native starch samples, and pre-gelatinized samples. We want to understand their effect of relative humidity with regards to the surface area, as well as the diffusion kinetics. So for the iGC-SEA method, experimental method, we carried out the experiment at 30 degrees and keeping the concentration in the range of the PET range. And we want to compare 0% relative humidity and 50% relative humidity. So in this case, just comparing a few properties of PET surface area with the traditional volumetric and the iGC-SEA and DVS, the DVS is quite similar to the nitrogen sorption technique in the range of its capability to calculate PET surface area. So we have from about 1 meter squared per gram to over 100 meters squared per gram. In the case of iGC-SEA, we can actually obtain PET surface area of very small surface area materials, so below 1 meter squared per gram. So this is very useful for products like drug products or fibers or hair excipients. The difference between our two instruments compared to the nitrogen sorption technique is the experimental temperatures, especially. So with nitrogen technique, we need to be under vacuum and also very low temperatures. However, with regards to the DVS and iGC-SEA, we can actually have it at ambient temperatures or even high temperatures also. And in case of the DVS, if need be, we can also introduce a vacuum to the system. For the nitrogen sorption technique, of course, you need nitrogen. However, the GVS and iGC-SEA, we can use other vapors, a range of different types of vapors. So like I mentioned, the nitrogen sorption technique carries out BT surface area analysis for quite higher surface area material. And if you wish to analyze materials below 0.5, you need to use krypton. In this case, we might find that because of these kind of extreme conditions of vacuum and low temperatures, it may completely dry out pharmaceuticals, or it may even break fragile crystals. However, in our iGC and DVS experiments, we can actually carry out our experiments at ambient room temperatures, and we can use various different probes. So you can use any N-alkanes, even cyclohexane. As long as the isotherm conforms to a type 2 and type 4 isotherm, then we can analyze and obtain the BT surface areas. So with regards to our DVS experiments, we carried out experiments with regards to water absorption. And in this case, we used the DVS resolution, and we carried out experiments at 25, 50, and 70 degrees Celsius, using 200 milliliter per minute of dry air. We also dried our samples for 10 hours. And we used relative humidity steps from 0% to 95% with 10% step increments. So I'm just going to show you the results for our BT surface area. So in this case, we have our partially gelatinized starch sample, and at 0% relative humidity. And the probe we've used is ethanol at 30 degrees Celsius. So we obtained a BT value of 2 meters squared per gram. So when we introduce humidity, in this case 50% humidity, water starts to compete for we have water starting to compete for the sites which are blocked. And in this case, what's interesting is that as humidity increases, the measured BT surface area also increases. So we have at 0%, we have 2 meters squared per gram, and at 50%, we have 5 meters squared per gram. And this trend can be observed for all our other different types of starch materials. Increasing humidity results in an increase of surface area. So the table summarizes the different surface area of the material, and we can see that the sample's increased surface area with increase in relative humidity. This can be attributed to the swelling of the starch. So also what's quite interesting here is that in the table, the NCS, which hasn't been gelatinized, and the modified NCS, which has been completely gelatinized, has a very high surface area, and also high surface area at both 0% and 50% RH. And the fully treated modified NCS is high even at 0%. And after exposure to water, as a result of swelling, the surface area increases even more. And this could be attributed to moisture acting as a plasticizer, which cause a reduction of the TG in these samples. So in this table here, we are looking at the activation energy and the diffusion coefficients. And the relative humidity and temperature increases the diffusion coefficient. So because we have now an increased surface area with regards to our relative humidity, we now have an increased diffusion coefficient. And this could be followed by the swelling of the porous structure from a more firmer structure. So at high temperatures, there is a sufficient thermal energy to overcome the activation energy barrier. And so now the atoms and molecules are now very free to move in and out of the system. this can actually result into a lower uptake of moisture. So this is one of the DBS plots obtained. So in this case, we're looking at a mass plot of starch at different temperatures. We have 25, 50, and 70 degrees, and it's showing the percentage change of mass of the water molecules so in the powder solid over time. So what you can see here is actually at 25 degrees, we have a higher uptake compared to higher temperatures, 50 degrees and 70 degrees. And this is because, like we saw before, the diffusion coefficients are relatively higher at higher temperatures. So atoms are freely moving in and out of the system, so that actually the sample can't retain as much moisture and water. And this is why we have relatively low uptake of water in these samples. So here we have 3 different plots. So we have at different temperatures. We have all 4 samples at 25 degrees Celsius, 50 degrees Celsius, and 70 degrees Celsius. And we can see that actually the graph shapes actually change with regards to increasing of temperature. And like I mentioned before going to the next step, we have to reach a certain amount of equilibrium here. So in this case, equilibrium takes a longer time to reach at 25 degrees. However, when you start increasing the temperature at 50 degrees and 70 degrees, this equilibrium is reached much faster, and the kinetics are much faster at these 2 temperatures. So just to conclude, the BT surface area was used used iGC-SEA, and this was carried out at 0% relative humidity, 50% relative humidity, and we saw there was an increase of surface area with increased humidity, and this could be actually swelling of the sample. With regards to the DBS, we carried out water sorption method for different temperatures, and we could understand the diffusion kinetics much better. And because of these diffusion kinetics, we can understand why there was a lower uptake of moisture of these samples. So thank you for listening to my presentations, and if you have any questions, please do let me know.
Thank you very much, Sabiyah, for that informative presentation. We are now open for questions, so if you have questions, please use the chat box or unmute your microphone. So I have here one from Millie. Can the samples be remeasured? How much consistence or disparities if the sample has been measured again or multiple times? Do I need to worry about the irreversible adsorption that damaged my samples?
Well, with regards to the samples that do swell, to obtain consistent results, it would be better to have a fresh sample each time, because once you run your humidity experiments, you've already introduced humidity onto your surface. And at this point, we've already made changes to the surface. So in this case, it's probably best to use a fresh sample if you want to test reproducibility. And in our systems, we have excellent reproducibility, lower than 1%.
Just a follow up, Sabiyah, how much sample do we need for IGC or DBS experiment?
So with the iGC-SEA, it's dependent on the BT surface area of your samples. So if you have a relatively high surface area material, such as activated carbon, you'd want to use very small amounts of material, so about 10 milligrams. However, if you have very samples with very small BT surface area, you want to use quite high masses, so around 100 milligrams. And for the DBS, we also use around 10 milligrams. However, if we have maybe a sample which is more hydrophobic, we may want to increase the mass. And also, if we have a relatively higher uptake and equilibrium is not reached very well, then we might want to lower the mass. So it's sample dependent, but it's around between 10 and 100 milligrams.
All right, thank you. I hope we answered that, Millie. Another question from Bruce. Pharma stability temperatures are typically 25 degrees to 40 degrees. Can you comment on the change of a DVS isotherm on excipients over this temperature range? If I generate an isotherms at 25 degrees Celsius, is it likely representative at 40 degrees?
Changes. Oh, sorry, 1 second.
If I may clarify on that, Sabiyah, I think.
Yes, sorry, carry on, Majid.
Yeah, Bruce is talking about glass transition temperature and the effect of humidity. Of course, the humidity changes and vice versa. As you increase the humidity, glass transition temperature changes. So you'd have to take into account the glass transition and the changes that might occur as a result of change in temperature and humidity. In fact, if you do the experiment, the same humidity experiment at different temperatures, you can plot a map of the stability of the material where changes of both temperature and humidity can predict the stability of your material.
Okay, thank you. I hope that answered Bruce. Okay. Another question from Ilham. Thank you for your presentation. According to the last slide, the temperature was more important factor than the type of material, since the graphs were almost identical in each temperature category. So what about the RH percentage? Does higher RH cause any effect like the saturation in affecting the sorption isotherm? What about the rate of introducing RH to the material?
So yes, that's correct. So with in this case for the starch samples, when you increase the temperature, we have the different graphs, and with all four, we have kind of similar plots. So in this case, when you increase when at each stage of relative humidity, equilibrium is reached much quicker. So the kinetics are much faster in this case. And so if you do maybe change the different steps, you will probably obtain kind of, if you go from, in this case, we're going from steps of increments of 10%, so you'd get a plot like this. But if you were to jump from 10 to 30 and then 50, you would expect the same kind of trend, but at different stages. And you can also have different experiments, such as ramping experiments. So you can go directly from 0% relative humidity to, say, 50% relative humidity in the space of half an hour. So there's also different types of relative humidity experiments you can do with your samples.
Okay. I have here, thanks for that, Sabiyah. I have here another question from Millie. I have a little difficulty to understand the mechanism behind the increased surface energy at high RH. Would the swelling take more cavity of the sample, leading to reduced surface energy?
The experiments we mentioned here are not to do with surface energy, they're to do with surface area. And in this case, when we introduce humidity, what we have is because the water interacts with the bulk of the material, causing it to swell, we have an increase of relative humidity. However, in some samples, this is not necessarily the case. We can have samples when you introduce relative humidity. If you're doing, let's say, ethanol molecule, they're competing with the sites for the water. So really what would happen, you'd have a decrease in surface area, and that's more common. However, in this case, our water molecules actually interacted with the bulk of our material, causing it to swell, and that's why we have a higher BT surface area.
Okay, a follow-up question from Ilham. Have you considered any RH above the 50%?
So in the experiments we've done from 0% to 95%. RH. So we have done above 50% in this case.
Okay, I hope that answers, Ilham. Another question from Raksit. Hi, Sabiyah. Thanks for your presentation. Why different kind of starches not showing any difference of moisture uptake event at different temperature? Does it mean they all behave the same? In your previous slide, starch 1500 has shown some difference compared to other starches. Can you please explain?
Can I just add that there are differences. If Sabiyah, if you could go to the previous slide where you have, yeah, no, the one after. Yeah, so as you can see at different temperatures, you for starch 1500, you see differences in uptake at as you go higher in temperature, the uptake decreases, and that's expected. As at higher temperatures you have higher molecular mobility, so there is more molecules moving in and out of the bulk of the material, and the net effect is that you'll have a lower uptake at higher temperatures. And this you see with a number of different materials, the same effect can be observed. With the other samples, yeah, you're right. The effect is less, and the uptakes are more similar at different temperatures, and that's because the material basically hardens after exposure to humidity. These are the more fully gelatinized samples, and basically with the initial gelatinization, the effect of moisture is taking place and the material has already hardened, and that affects the uptake of the material as well.
All right. Is that answer the question, Raksit? Okay, probably yes. So is there are there any other questions? Yes.
I believe yes, and thank you for that answer, Majid and Sabiyah. Really nice presentation. But if you go back to one slide that you've shown and further back, if I can ask you one more question, follow-up question, if I can, one more slide back where you see, yeah. So what you analyze and what you derive when you expose this sample at a different humidity? Is that the diffusion coefficient of starch is different than any other sample?
Well, what we see is here at different relative humidities, we see the differences in the diffusion rate for different samples. So as degree of gelatinization increases, then you see basically similar effects in the diffusion kinetics. And as I said, as the temperature increases, the molecular mobility increases, and then you see diffusion, increased diffusion in and out of the sample. So yes, obviously you see the differences at higher humidities and also at higher temperatures.
And that's what I wanted to, I expected in your last slide, because of diffusion coefficient differences at a different temperature. Why that was not materialized when you have the last slide where I think, like, effect of temperature shows almost overlapping phenomena. So that was the confusion, but I'll look into much more detail. And thank you for your answer.
Yeah, I mean, we can discuss that further offline if you are interested. We have more results, but it's just at the end of the day, it's just the way the material. We have some video images of the material, and work is still ongoing to investigate the effects. But actually, it shows the material is almost caking, and that is part of the reason.
Okay. Well, thank you. I'll definitely look forward to talk to you offline.
Okay, thank you.
Thank you.
Okay, thank you, Raksit. Are there any other questions from our participants?
Hello, this is Bruce again.
Yes, Bruce, please.
And the next slide, go down or down one. So that was actually the question I was asking, and I'm sorry I missed it during the presentation, but it's the impact of temperature on the isotherm. So you run it here at 3 different temperatures, and my question was in the 25C to 40C range, which is typical in pharmaceutical industry. How much of an impact on the isotherm are we going to see? So it wasn't necessarily about the glass transition, but the change in the mass of water that's absorbed as a function of temperature.
Well, as a function of temperature, it all depends in the nature of the material. But as you say, for pharmaceutical materials, you would mainly work at room temperature.
Well, when we put materials up on stability, we usually measure the isotherm at room temperature, 25C. But then if the samples are put up at 30C or 40C for stability testing, then the isotherm would presumably change, but how much of a change? Is it a significant change? And I suppose that's a kind of loaded question. Is it a significant change? But
yes, it would be. I mean, are you talking about 0% relative humidity and increasing just the temperature, or at different humidities?
Yeah, the full isotherm, just as you pictured, just as we see here.
At the full isotherm, yeah. Yeah, well, then that you should see a significant effect. And in fact, there is a method. What you see here is a step type method where the humidity has increased step by step. Now, if you do a ramping method, you'll see the changes. You can, for visualization purposes, you see the effects more clearly. And again, with the ramping rate as well, if you increase the ramping rate, you'll see the effects even better, more clearly. But you might not be able to measure the exact RH as accurately as if you do it with a slower ramping rate. So it's quite interesting. We have application notes on that, which demonstrate to you how the effect of the ramping rate and also the differences between the ramping experiment and the step experiment.
Or could I say you could do an ISO-RH experiment? So then just pick 50% RH and do 25, 30, 40C and get a fair idea of the expected change.
Exactly. Yeah, that's another way of looking at it. Exactly. That's absolutely right.
Okay, that's good to know.
The only thing is it depends on the type of the instrument as well. We have DVS intrinsic, which ranges in temperature from 20 to 40 degrees. And of course, you can do that. You can keep the relative humidity constant and change the temperature. But with the other systems where there is an incubator, that's a bit more difficult to do, because as you increase the temperature, the balance of stability changes and the data becomes noisy. So we wouldn't be able to do that experiment with the DVS resolution, for example, or DVS adventure, but DVS intrinsic would be ideal for that purpose.
I see. Yeah, we have a resolution. So yeah, that you're requiring the whole incubator to increase in temperature and the water bottle to.
That's right. Yeah, that wouldn't be really possible, because that affects the temperature, the stability of the balance. Yeah.
I see. Okay.
If I could ask a question on this curve as well, something I don't quite understand about it. The red curve, the 25 degrees curve, is doing what I might expect, which every time you change the humidity, a sudden increase in absorption and then a slow increase to where it's near equilibrium, and then you change it again. So you have these scallop shapes going up and then the reverse going down. But in both the other two curves, at 50 and at 70, we have, at least at the start, it seems to make sense. There's like a rather rapid climb, but there are a number of places where you seem to have allowed it to plateau for some reason. I'm not sure why. So I'm wondering why those plateaus are in there, and I'm even more wondering why those plateaus seem to be going down in a number, even very early at maybe 500 or 600, or 700. One of the early parts in the 70-degree curve is clearly dropping. And later on, near the summits of both the 50 and the 70, they are clearly dropping. And what is going on there?
And that's a good question. I have the same problem or issue trying to understand that myself. So please.
A very good observation. Thank you. That's something we were discussing earlier with Sabiyah. As you increase the temperature, it's due to the evaporative cooling effect. The temperature of the water changes, and that affects the basically the concentration generation, and then the uptake obviously is affected. So then first, to begin with, you see an increase, and then at each particular step, especially if you go to 70 degrees, this effect is more observable. You see a dip in the generation, and also if you plot the generation, in fact you see a dip, and at the same time you see a dip in the mass uptake as well. So this is due to evaporative cooling, which you can't really do much about it, but my colleagues are working on a heated reservoir at the moment, and watch the space. Soon you'll see a heated reservoir, which is meant to take this effect away, and this will be a basically pioneer technique as well.
Well, thank you.
No, that is really great explanation, Majid, and thank you for that, and thank you for sharing question. I have one follow-up question onto that. Where do you see evaporative cooling more, and where do you see the pronounced effect? Which are the ranges, or which humidity cycle where you start to see the evaporative cooling effect?
Yeah, it's all to do with the reservoir and the head space. We have tried different, we have taken different measures to reduce that. One is by increasing the size of the bottle, and then increasing the volume of the liquid in the reservoir. But as you say, there is a particular sort of relative humidity which is towards the higher end of the relative humidity generation. You see more of this effect. And of course, at higher temperatures, at above 50 degrees, again, this effect is more. So we've had, when you do the experiments, some of our customers typically do 85 degrees, 85% relative humidity, and that effect is more pronounced at 85 degrees. And like I say, at above 50% relative humidity, you see more of this, and gradually, the higher you go, the more of this slope you see. But again, that's something we could discuss later, and I can show you more data, and maybe I can share with you a presentation later that shows the generation, how the generation is affected, and you see that effect more pronounced there, where the generation is plotted.
Sure. Thank you so much.
And this is Bruce again. I'd appreciate seeing that presentation or receiving it by email, whatever.
Okay, I'll get your email addresses from Zen and then forward you the presentation. I'll have to check with my colleague whether at this stage it's not a company confidential, because we haven't released the data yet. But surely I can send you some slides, some information.
Great, thank you.
Thank you very much. Are there any other questions from our participants? All right, I think that's about it. That concludes our webinar today. If you have any questions later on, you can always email us at science@surfacemeasurementsystems.com, or visit our website at www.surfacemeasurementsystems.com. Thank you very much for your time today. Thank you so much to Sabiyah and to Majid, and we hope we will see you, speak with you again in the following webinars. Thank you. Thank you for your time.
Thank you, everybody. Bye-bye. Have a good day.
Thank you. Bye-bye.